We're continuing through section 3.4 general annuities. This time we're going to deal with interest less frequent than the payment. So here, instead, before we looked at this before, we were using EIR because compound interest was paid for part of a period. So now we're going to use simple interest. So just as a review, our simple interest, remember we had P over here, S over here. If we're moving forward, we get S equals P times 1 plus RT. And if we're moving backwards, we get P equals S over 1 plus RT. Okay? Usually when we're dealing with this, we move everything forward to the end of the period, but it's always good to review. The other thing that we need here is we're going to be adding a bunch of T's together. So it's just helpful to know that if we add 1 plus 2 plus 3 all the way to n, that is a handy sum. It's n times n minus 1 all divided by 2. Okay? So if we want to add those all up and go a little faster, we're able to, which is really handy. Alright, so let's look at an example so you can kind of see what I'm talking about. So we're going to do example 34. So in example 34, we have payments of 60 are made at the beginning of each month into an account that pays interest semi-annually. So already here we have a conflict because we have months semi-annually. Find the value after 6 months if simple interest is paid for part of a period. So we look here, we're made at the beginning of every month, so this means we make one now, 1 month from now, 2 months from now, 3 months from now, because it's only 6, I'm just going to do them all, 4 months from now, 5 months from now, and then at our 6 month mark. So here's where we're moving them all. So we're going to move this one forward 1 month, this one 2 months, 3 months, 4 months, 5 months, and 6 months. Okay, because we're trying to get the lump sum over here. So we're going to call that X. Okay, that's what we're trying to find. Because we're doing after 6 months, so that means the end of 6 months. So after kind of indicates the end. Okay, the end of 6 months. So our rate is still 0.05. Anytime that we're dealing with this, when we're looking at our rate, see here it says 5%, so we know we got the 0.05, but it's compounded semi-annually. When we're dealing with the simple part, we're not going to change the rate, it's going to stay the same, and then we just count them up with the months, and T is always going to be in years. Okay, so I'm just going to add that up here, T in years. Okay, that's the big idea. When we're dealing with simple interest, T is always in years unless it specifically says otherwise. Okay, so then what we're going to do is now we just set this up. So X is going to be the sum of 60 times 1 plus 0.05 times 1/12. So that's this one right here. And then 60 plus times 1 plus 0.05 times 2/12. I'm going to write out the big long thing here, and then I'll show you the condensed version. Okay, so 2 months would be the payment from the beginning of month 4. 3 months would be the beginning of the 3rd month. 4 months would be the beginning of the 2nd month. Then our next one would be 5 months, so 5/12 of a year, and then when we're all done, 6 months, so 6/12 of a year. We'd add that all together. So that's kind of a bear to enter because there's just a lot going on. So again, we're going to do the shortcut method using the summation formula. So it'd be 60 times our count of payments times plus 1.5 times 1 plus 2 plus 3 plus 4 plus 5 plus 6 months. Okay, so when we do our count, we have 1, 2, 3, 4, 5, 6. So this is 6. Okay, so this is the number of payments. Okay, and then this is all the months added together. So the sum of months of each payment. Okay, so we didn't put that whole mess in our calculator. So here we got the calculator. So we do 60 times 6 plus 0.05 times, and then you can make the calculator do it. 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 12. So again, I use a second set of parentheses for that. So we get 365.25 would be our semi-annual payment. Okay. Now just to show you that 1 plus 2 plus 3 plus 4 plus 5 plus 6 and using this summation formula, I'm just going to do that over here. So that's a sidebar. Okay, so when you do that straight in your calculator, you get 21. Okay, so you can confirm that if you want to. So now I'm going to use the summation formula just to show you how it's the same. So our n here would be 6. So n minus 1 is 5, and then we divide that all by 2. Sorry, it's supposed to be n plus 1. My bad. So it'd be 7. So it'd be 42 over 2, or 21. Okay, 21. So I'm just going to pause for a minute, so if you need to pause before we start the next example. Okay, so we're going to go ahead and start example 35. So this one is a very similar problem, similar setup, but it's going to work a little bit differently. So the idea here is we're trying to find the present value of an annuity. Present value means we're looking for the beginning value, so that's going to be A sub n. That pays $625 at the beginning of each month for 9 years if the money is worth 7.7%, compounded annually with interest paid for part of a period is simple. Okay, so we have again kind of two timelines here. So first we're going to make our payout timeline. Okay, so we know we're trying to find A sub n, that goes at the beginning because we're trying to find the present value of an annuity. That tells us it's A sub n. The money is worth 7.7% compounded annually. So those are the pieces that we need. So that means in 1 year we're going to have R, and then 2 years later we have another payment, and we're doing that 9 times, so we know that n is 9. Okay, so we're trying to find A9. The money is worth 7% annually. That tells us that R is 0.077. So I is going to be 0.077 over 1, because annually would be once a year. And interest paid for part of a year is simple. So we have to deal with the simple piece. Okay, the simple piece. So the simple has to do with the 625. So I'm going to make a separate timeline to deal with my simple. So this is the beginning of every month. So we'd get one now, because it'd be beginning of month, and then we get another one next month, and another one next month. Okay, last one of the year is going to be at the 11-month mark, and we need to do it for 1 year, so we're going to move everything to the back. Okay, so we're trying to find this value. So again, we have to move them just like we did up here in number 34. We have to move them all the way down. Okay, easier version of the formula. So R is going to be 625 times, we're going to make 12 payments total, plus 0.077, and this is going to be 1 plus 2 plus 3 plus 4 all the way to the 12. So it's going to be 12 times 13 over 2 using that summation formula. So 625 times 12 plus 0.077. 12 times 13 gives us 156. 156 divided by 2 gives us 78. So times 78. And again, that whole thing is over 12. Because that's the number of months that we're dealing with. So when we plug that in our calculator, so again, just to show you this again, 625 times 12 plus 0.077 times 78 over 12 is going to give us 7,812 and 82 cents. because it's payment, so we're going to round up to the nearest penny. Rounding up, okay. Round up for payments. Okay, and then we're going to take this number and we're going to bring it back over to this timeline because now this is our R. So I'm going to switch colors here, and this would be our 7812.82. So now we're going to find A9, R7812.82 that we just found over here, times, now we just use our A sub n formula, so 1 minus 1 plus I, our n is 9, so to the negative 9 over our piece. So then plugging that in the calculator. Okay, so again, make sure that you have parentheses around your whole numerator, and then you need a separate set of parentheses around your 1 plus I. Okay, exponent should be negative here. So A9 is 49,420, and here we round to the nearest penny, so 58 cents. Okay, for payments we round up, otherwise it's to the nearest penny.